The University of Melbourne, the #1 ranked university in Australia, #31 in the world, and ranked 7th for graduate employability worldwide. And the Trinity College Foundation Studies program can get you there. Successfully meeting the University of Melbourne's requirements during Trinity's Foundation Studies program provides you with guaranteed entry into undergraduate studies at the University of Melbourne. In fact, it's the only pathway that offers a guaranteed entry to the university. Once you're there, you can choose from over 100 major fields of study, so you can pursue the career you want or explore different subject areas until you find your passion.
One of the main difference between foundation studies and high school is the integration of lectures. So here we don't do big classes. Instead, we break it up into lectures and tutorials. And by the time that they enter uni, it feels like they've been doing all this already at Trinity the whole time. So it prepares the student really well for their life at Melbourne Uni.
Join us at Trinity College today, your pathway to the University of Melbourne.
And a very good afternoon to everyone who's joined us for tonight's live lecture, the Trinity Talks series that we're bringing you live from Trinity College. My name's Ben. I'm one of the managers at Trinity College in the Foundation Studies program.
Would you like to invest in the hottest IPOs as a retail investor? It's not as difficult as you
would. Sorry about that. And tonight we have a fantastic lecture lined up for you, which includes 3 of our leading lecturers in physics, biology, and chemistry. I'll introduce them shortly. Tonight's lecture is about how do we see colour? What is colour and how do we perceive it? I'll introduce our lecturers shortly to you. Before we do, just a little bit of information about who we are here at Trinity College and what we do. Firstly, the University of Melbourne, Australia's #1 ranked university and currently ranked 33 in the world. This is an amazing ranking. This puts Melbourne University bachelor degrees amongst the best in the world and of course continues to be Australia's #1 ranked university, a great place to study. We're focusing on the sciences tonight, and at Melbourne University, there are a whole range of different specializations in science that students can pursue. 42 of these major areas in science are studied within the Bachelor of Science. Those are some of the areas that you can specialize in the Bachelor of Science on your screen at the moment. But of course, also sciences relating to medicine and medical sciences. So the Bachelor of Biomedicine. There are 15 major areas of study within the area of biomedicine. So an excellent place to study sciences and to specialize in any of those areas that you've just seen. Okay, so before I introduce you to tonight's lecturers, a few things. Firstly, we've got another big crowd joining us for tonight's lecture. We're about to tip over almost 500 students in the next minute or two. So of course, a few ground rules. Firstly, we'd love to hear your comments throughout the lecture. Our academics would love to hear from you. So if you've got any comments or questions relating to the topic, please put these into the chat, okay? Anything related to the topic that our academics are talking about, put it into the chat. Okay, our academics would love to hear from you. They'll ask some questions and they'll want to hear from you. If you've got any other questions related to how to apply for Trinity College, how to apply for Melbourne University, scholarships, entry requirements, or anything else related to the University of Melbourne or Trinity College, please put this into the Q&A function. The Q&A function you'll find on your Zoom account. My colleague, James, are you there? James Curley from Trinity College will be with us behind the scenes, managing some of your questions that you have. So James, having a look at the attendees, where are the students coming from tonight?
We've got a really good mixed bag. We've got quite a few from Vietnam, Ben. We've got some from, I can see the Philippines there. We've got some Indonesian students with us, and further afield, some looks like South Asian, possibly Bangladesh or Pakistan. So we've got a really good mixed bag. I'm sure a lot of you have joined us in the earlier lectures last Monday and the Monday before that. This is number 3 in the series. So welcome back. And for those of you who are here for the first time, you're in for a treat. I hope you enjoy it. I'm sure you will. If you've got any questions related generally, as Ben said, generally to study in Australia, Trinity College, the University of Melbourne, put them in the Q&A section and I'll answer them in the background. But if you're answering and interacting directly with the academic staff, pop them straight into the chat, not the Q&A, because the academic staff won't be monitoring the Q&A. They'll be looking at the chat. Okay, have a good session and I'll get into the background. Thank you, Ben.
Thank you very much, James. And James will be behind the scenes answering your questions and helping me manage. You know, there's such a great bunch of students. We've gone over 500 now. A few other things. Any comments that you make, keep it respectful and also keep it on track. Okay, we don't want to hear what you're doing on the weekend, and we don't need your Facebook link or anything like that. Keep it your chat comments relevant to the topic. Okay, and finally, in English, we're going to be presenting in English tonight, so we'd appreciate your comments in English also. One final thing before I introduce our academics. If you have been given a link for tonight's lecture from your teacher or from your friend, please note that you won't get a certificate, okay? Because we don't have your name and we don't have your school and we don't have where you're from, okay? So to get the certificate of participation in this lecture series, you do need to register yourself. I noticed that there is a lot of students with the same name, which tells me that that a friend or a teacher has shared the link with you. You will not get a certificate unless you register. Okay. We'll be running a question and answer at the end of tonight's lecture, but without any further delay, let me introduce you to 3 of our senior lecturers at Trinity College who have been with us for quite some time. They're experts in their field. Dr. Kerry, Dr. Kathy, and Dr. Fawn. How are you tonight, guys? It's great to have you along. I'm going to hand over to you now. Have a great lecture, guys, and I'll see you at the other end. Bye for now.
Good afternoon, everyone, or good evening, wherever you are. I think I see someone from Germany, so good morning. My name is Dr. Fan Lai, and I'm the subject leader for physics at Trinity College.
Hi, everyone. It's an absolute pleasure to be here. My name is Dr. Kerry Higgins. I'm the subject leader for chemistry and biology in the Foundation Studies program at Trinity College.
And my name is Kathy Symington, and I'm one of the lecturers in biology. And it truly is a delight to have you all with us today. So we're going to be exploring some amazing things about the world of colour. Isn't colour just extraordinary? Well, like Ben said, there's going to be some times when we ask you some questions and ask you to message in. And I'm going to start by asking you one of those questions, which will come up when we see the next slide. So let's start to message in. What do you see on this slide? I mean, I know it's dots, but message in, tell us what you see. Excellent. You can all see the number 12. Fantastic. And that's exactly what you should see. This slide is what we would call a control slide. It's something that everyone should be able to see. But let's see what happens when we look on the next slide. Let's get some messages in about what we can see here. We're getting lots of people saying 74, lots and lots and lots. So fast, I can't even see your names. In fact, I'm about to tell you something very interesting about this slide. This slide is part of a test series. Most people actually do see 74 exactly as all of you said. And when I say most, the percentage that it is approximately 91 to 95% of all people. And that's what we would call normal vision. But would you believe me if I told you some people see a different number? They see the number 21. And we could even predict what kind of people are likely to see that. It's mostly men. And if it's Caucasian men, it's about 8% of them. If it's Asian men, about 5%. If it's African men, about 4%. And for women worldwide, it's about 0.5 to 1%. You see, what these tests do is help identify colour blindness. And for the people that see the number 21, what they've probably got is red-green colour blindness, which makes it hard for them to see red, orange, yellow and green. And what explains there being more men affected than women is that it comes from an error in a gene on the X chromosome.
So most of us see a world full of vivid colour. But did you know that not everyone sees the same? For some people, some of the colours are missing, while for some others, they see a world in black and white. Today, physics, chemistry and biology will come together to explore what is colour, how do we see it, and some of the things that can go wrong. So let's start that journey by considering what is colour. And to do that, I'll hand you over now to Fun.
Thanks, Carrie. So what is color? What does it mean by red color or blue? Now, we know that objects can only show colors when there is light. Without light, they will appear dark or grayish, like when you are in a dark room or at night. So to detect color, light in the form of photons must enter our eyes. And each photon has a property known as wavelength. It is this wavelength that will determine the energy of the photons and the color we see. So let's look at the rainbow first. The rainbow colors makes up the visible range in the electromagnetic spectrum. This rainbow spectrum can be divided up into about 6 color bands. And most of us will start seeing some really dull red at around 740 nanometers. As this wavelength decreases, the color changes gradually from red to orange, yellow, green, blue, and then finally violet at around 380 nanometers. Now, the photons giving us the red color has actually less energy than those for the blue color because of this equation, E equals to hc over lambda, where E is the energy of the photon, h is Planck's constant, c is the speed of light in vacuum, and lambda is the wavelength that we are looking at. So now the 3 primary colors of light actually are just red, blue, and green. The other colors we see in the rainbow spectrum can be created by various combinations of just these 3 primary colors. Now, and by mixing these primary colors in equal proportions, we get the secondary colors, the yellow, cyan, and magenta, as shown in this slide here. Now, the primary colors are used to project images on your television screen and your computer monitors. So if you have a magnifying glass at home, you put it very close up to your computer screen, you should see them. But what about objects then? How are they colored? Objects have color because they contain pigments. A very common pigment is the dark green pigment called chlorophyll, which is found in plants. And pigments are found in all manufactured objects because pigments are used to give colors to paints, dyes, and inks. So now a question to the audience. A color printer needs just 3 colors of ink to print all colors that we can see. Can anyone tell me? Wow, that was quick. No, we just need 3 colors. Okay. I see quite a few. Oh yeah, there's some answers there, but all right, let me just get back to my next slide. So the primary colors of pigments are the same as the secondary colors of light, as shown in the next slide. So remember, the secondary colors of light is your cyan, magenta, and yellow. But these are the primary pigment colors. And by adding these 3 primary pigment colors, we get all the other colors. So you can also try this at home if you have a color printer and some printable transparencies. All right, print 1 primary color on 1 transparency of the same image and 1 in black and white. And then you overlap them, okay? And you get the final image and have a look. Now, this technique is very similar to the block printing method that was used in the 19th century.
Thanks for explaining to us how colour works out in the world fun. Can you say a bit about how we see colour?
Yes. So now let's look at how we see color. Let's look at an opaque object first. What is an opaque object? An opaque object is one that does not let light through, but will reflect and absorb light. So the color of an opaque object is made up of the wavelengths of light that has been reflected. So for example, the red pigmented object shown here, okay, will absorb all wavelengths except the red. So the object appears red. All right, so the absorption and reflection of wavelengths is determined by the arrangement of electrons in the atoms of the pigments. So what happens when light is directed onto an object? Remember, light are photons carrying energy according to the wavelengths, and objects are made up of electrons, protons, and neutrons. Now, I'm sure a lot of you would have heard about Niels Bohr. According to Niels Bohr, the electrons are arranged in orbits around the nucleus. And these orbits are at fixed distances from the nucleus. The distances depend on the structure of the energy levels and the type of atoms that makes up the pigments. So, and these electrons can jump from one energy level or orbital level to another. So incoming photons will be absorbed by the orbital electrons only if the photons carry energy that is equal to the energy difference between any 2 orbits or any 2 energy levels. So these photons, once absorbed, will never again be released in the form of light. The photons of other wavelengths that have not been absorbed will be reflected or scattered, and thus giving us color. So if an object absorbs all wavelengths except blue, the object will appear blue. Tomatoes are red because the red carotenoid pigments in the skin absorb photons of all wavelengths except those of red, which are reflected back to our eyes. Now, the color of light that strikes an object will also affect the color that will be perceived for that object. What color would a white car be under red lighting? So you can see, as you can see here, a white car will appear red under red lighting, and a blue car blue under blue lighting. So a sky blue car will appear sky blue under white lighting because the car will absorb all wavelengths except the blue and green, which are reflected into our eyes. The same blue car will appear black when red lighting is used because the car will have absorbed all the red wavelengths and none will be reflected. So the color we see also depends on the amount of light reflected by an object and how it is reflected. Why? Because this would determine the amount of photons entering our eyes. So specular reflection is defined as the light reflected from a smooth surface at a definite angle. So for a smooth surface like a mirror, virtually all the wavelengths are reflected equally into one direction. Diffuse reflection, however, is produced by rough surfaces that tend to reflect light in all directions. So for a rough surface, each individual ray, when it strikes the surface at different points, as shown in the next slide, each point has a different orientation. And so the normal, right, the dotted lines that you see, is different for each ray, which means the direction of the reflected ray will also be different. You can see from this simulation, all right, that shows, all right, what happens when light hits a surface. The rough magenta surface will reflect the red and blue wavelengths into different directions because it's magenta color, so it's red and blue. For a smooth magenta surface, then all the red and blue wavelengths will be reflected onto only one direction, and they will recombine to give the bright magenta color. So an apple appears shiny because it has a smooth surface that reflects all wavelengths into our eye. A red ball of the same hue as the apple will appear dull because the light will be reflected in all directions because due to the surface not being as smooth, and only some of the wavelength will enter our eye. The color also will appear differently under different viewing conditions. For example, the color of water. A glass of water appears colorless, correct? But when white light is shone through a column of water, the liquid is a bit bluish and it becomes darker, deeper green as the depth is increased. So due to the vibrational energy levels in the H2O molecules, the water absorbs the longer, redder wavelengths, scattering the blue ones. And so if the water appears bluish. And you may think that the water in the ocean and the outdoor swimming pool appears blue because of the reflection from the sky. But what about an indoor pool? Right? So an indoor swimming pool appears blue from above because light reflecting from the bottom of the pool travels through enough water, right, that all its red components are absorbed. Varying depth of sea floors also influence the reflection process. The reflected light from different depths will interfere when they emerge above the surface, giving it various shades of greens and blues. So interference of reflected light also comes into play here. Now, so we know what is color and how we see color, but how do we actually see color? Maybe Kathy can help us there.
Sure, Fun, thank you. And I think you've given us a few clues along the way. Like as we were watching, who saw on some of Fun's diagrams, there were pictures of eyes. Of course, the answer to Fun's question is in our eyes. So let's look closely inside and see what structures there are inside the eye that can help us to see colour. So on this diagram, starting on the left, we have a cross section through a human eye, or at least a diagram of one. We can see light coming in through the front of the eye and hitting a layer coloured purple on this diagram at the back of the eye, and we're about to discover its name. That's the retina. The biggest part of this diagram is an expansion of part of the retina. And when we look closely in there, we can see a line of long, thin cells. Many of them are coloured in grey, and we're about to discover their name. They're called rods. You probably saw 3 different cells. coloured green, red and blue. They're obviously not that colour in real life, but we'll see what that colour means soon. And they have the name of being cone cells. So let's find out a bit more about these cell types. So what we'll see on the next slide is, again, we're talking about the retina, the layer at the back of the eye. We've seen two cell types, rods and cones, but now we can start to see what they do. Rods help us to see black and white, while cones help us see colour. And did you see here how many rods you've got? 120 million. And they're mostly around the edges of the retina. But look, for the cones, only 6 to 7 million, responsible to see all the colours in the world, and on an area so small, only 3 millimetres across in the middle of the retina. So let's find out a bit more about these cell types. So as we see here, we can see a diagram of rods on the left and cones on the right. And there are really interesting shaped cells. There's nothing else that looks like these cells. But there are some things here that I think are familiar. Did you see there's a nucleus in both of these cells? And did you see the mitochondria as well? Oh, I wonder who's going to say what mitochondria do. Who's going to quickly type in, what do mitochondria do? Who'll be the first? Energy. Excellent, Eric. Powerhouse of the cell. Every cell needs energy. So thank you for those of you who've said, and these cells are no exception. But did you also see near the bottom of the diagram two other structures, axons and synaptic endings? Who can say what cell type that reminds them of? Who'll be the first? Nerve cells, Learnley, fantastic. And Maria Angela, brain cells have them too, very good. So this is going to be the point where the rods and the cones connect with nerves to send signals into our brains. The top part of what's on this diagram, labelled the outer segments, we're going to find out about them later. But for now, let's find out a little bit more about cones. So there are 3 types, and we got a hint for that in an earlier diagram, and they're named according to the colour of light they detect: blue, green, and red. 64% of our cones detect red, 33% green, and only 2 to 3% detect blue. Now, you might be wondering how we see all the colours in the world with just these 3 cone types. Well, I can say a little bit about that on the next slide, where we connect the biology with the physics. The blue, green, and red that is detected is the primary colours of light that Fun explained to us earlier. And our brain is able to detect what percentage stimulation the different cones have got and work out for us exactly what the colours are that we're seeing. So we've heard about the physics of light. We've heard a little bit about the cells, but it still seems there must be more to the story. Kerry, is this something you can help us with how do we see colour?
It certainly sounds like it's my turn to step in and explain a little bit about the molecules that are involved in this whole process. So Kathy has introduced us to the cone and the rod cells. These are the cells that allow us to see. But how? How do we see? How do we detect the light that Fun was talking about? Well, it all comes down to the regions that are the outer segments of these cells. So you'll see those outer segments and you'll notice that there seem to be lots of folding in these outer segments. So there's lots of membranes there. The molecules that actually allow us to see are found in these outer segments and found as part of these membranes. So let's start with the molecule that I think we should consider the absolute star of the show, the molecule that allows us to see. Its name is 11-cis-retinol. So without 11-cis retinal, you would not be able to see. So we better have a look at this molecule and see what this very important molecule looks like. So here it is. Da-da, chemistry. It's a small organic molecule. The structure I'm showing you here is a skeletal representation of the molecule. In the skeletal representation, we don't see all of the atoms shown, but you need to imagine that at each of these points, there's a carbon atom and the appropriate number of hydrogens attached to it. I love chemistry, so we better have a little bit more of a look at the chemistry of this molecule as we move on and explain what it does. So let's look at the structure. We start with a cyclic structure at this end, and then this long chain. And the long chain follows all the way down here to a functional group. See the functional group at the bottom? A question for the chemists out there. Can anybody tell me what is the name of that functional group? Anyone? Not seeing too many responses at the moment. Hydroxyl? Another guess? Anyone? An aldehyde. Ah, now it's coming up. Aldehyde. That's an aldehyde functional group. Well done. Well done. That was a bit of a tricky question to throw out there to start off with. That's an aldehyde functional group at the end of that chain. Okay, the other thing you might notice on looking at this structure is that as you look along that chain, you see a number of what are carbon to carbon double bonds. Now, carbon to carbon double bonds exist in two forms. They can be in the trans conformation or the cis conformation. Most of the carbon-carbon double bonds in this chain are in the trans conformation. There is one bond that is in the cis conformation, and that's the one that this molecule is named about. So on the next slide, I've labelled or circled exactly which one that is. So you can count the number of carbons from the start of the ring all the way along to carbon number 11. And here you see a carbon-carbon double bond. This gives this molecule its name. This is a cis bond, and this molecule is 11-cis retinal. So the way this molecule works is all based around this bond. 11-cis retinal is a chromophore. That's a molecule that is able to absorb light. Just go with absorb light. When it absorbs light, it undergoes a conformational change. So let me show you on the next slide just what happens. That conformational change is around that cis bond. So when you have free 11, when you have free 11-cis retinal, if light shines on it and that light has a particular wavelength of 350 nanometers, it causes a change in the conformation. You see we go from that cis bond here to a trans bond. Now you'll notice the molecule here is rather folded in shape. And so it's kind of folded down and around like that, if you can see my hand. When this change occurs, the molecule springs out and becomes straight, as you can see. And that's quite a big structural change for this molecule. So 11-cis retinal is a chromophore, collects light and changes conformationally when that occurs. A number of living things are able to see. They include the arthropods, that's the insects, the crustaceans, the spiders and the ticks. That includes the mollusks, like this lovely snail with its eyes at the end of these long tentacles. And it also includes the vertebrates. And of course, we are vertebrates, so that includes us. So all of these living things are able to see. And you can imagine from looking at these pictures, the structures of the eyes for each of these living things are quite different. But one thing they all have in common is they all use this molecule 11-cis retinal to collect light. So what makes this molecule so good? Well, firstly, as we've seen, it's sensitive to light. It changes in response to light. sensitive to light, but it's very fast. And that's important for vision. You think about what your eyes are able to do. You can look around or you can see images changing all the time. You need this molecule to be fast. And when I say fast, this is really fast. It changes in the matter of a picosecond, 10 to the minus 12 seconds. So it is incredibly fast. That's important for vision. The other thing that makes this molecule so important is it is incredibly stable. In the dark, it doesn't change. And that's really important for us as well. If we had this molecule that was flicking between conformations, we'd be seeing false images all the time. That wouldn't work for us. That wouldn't work for the insects, and it wouldn't work for the mollusks either. So it's really important that the molecule is stable. The other thing about 11-cis retinal that I've mentioned previously is you see that big structural change. And I'll show you in a minute why that's so important in us being able to see. So there's a structural change. And finally, for 11-cis retinal, for living things that use it, we need to be able to make it in our bodies. And to make it in our bodies, we need to be able to obtain the precursor molecules to make it from. And it happens to be that the precursor molecules are readily available in the environment. They're found in plant materials. And one of the precursor molecules that I'm sure you will be familiar with, or at least heard of before, is vitamin A. So this is the structure of vitamin A. And you might recall from earlier slides, it does look quite similar to the 11-cis retinal molecule that we've looked at so far. So vitamin A is a precursor molecule for 11-cis retinal. And we find it in all red, orange, yellow fruits and vegetables. When I was young, which is quite a long time ago, my parents used to say, you should eat your carrots. They're good for your eyesight. And I used to think, they're probably just tricking me, trying to get me to eat carrots. But actually, it's true. Carrots are a really great source of vitamin A. And you need that vitamin A as a precursor molecule to make your 11-cis retinal.
Now, Carrie, can I have a question here? I still don't really understand. You say that cis retinal can only be activated at 360 nanometers. So how we see all those other colors, the red and blue, which actually lies above that wavelength?
Mm-hmm. Very good question. Very important to answer. So there's more than just 11-cis retinal involved in this process. We also have a number of proteins that are really important. And the one that is most important in this process, or the group of proteins that is most important, are these ones, the opsin proteins. So this is a representation of an opsin protein. Proteins are made up of amino acids, and each of the circles in this diagram represents an amino acid. So this is a big protein. You can see starting down here at 1, and if you follow all the way through, it ends up at 348. So it is a protein that is made up of 348 amino acids. It's a big protein molecule. And so these opsin proteins are also involved with our ability to see. We find the opsin proteins, if we go back to thinking about our cone and our rod cells, we find the opsin proteins in these outer segments. As I said, there's lots of membranes there, and the opsin proteins are actually embedded in the membrane. So these orange and blue structures represent the membrane, and this represents the protein itself. Now, this type of representation is called a ribbon diagram. And you see, it's a really lovely way of describing the three-dimensional structure of a protein. You see these wonderful helical structures. And for the opsin proteins, there are 7 of these structures. Associated with this opsin protein, you'll see this little black structure in here. This is actually our 11-cis retinal. So 11-cis retinal binds to the opsin protein. Let me just show you on the next slide another representation of opsin protein in here with our 11-cis retinal, but just to show you that it actually binds, it makes a chemical bond with one of the amino acids. Protein. So the 11-cis-retinal binds to the opsin protein. Okay, so with all of that, still, how does that work to allow us to see the different colours? Well, there are different opsin proteins. And in fact, for the cones, where we have 3 different cone types, there are 3 different opsin proteins. And the opsin proteins differ in their amino acid sequences just slightly, just maybe 15 to 20 amino acids different. But that's really important because those differences affect the wavelength at which the 11-cis-retinal changes. And that means that each of those cones then responds to a different wavelength. And that's why when we look at the cones, we see that the red cones, as we call them red cones, have an absorption in a wavelength range that shows red. The green cones, green. The blue cones in that blue region. And that's because, as I said, the different opsin proteins affect the wavelength at which 11-cis-retinal undergoes that change. So we have our opsin protein at the top here, the red one, and associated with it is the 11-cis-retinal. Light of a particular wavelength will strike that protein, and depending on the cone that it's in, it can cause the 11-cis-retinal to undergo that conformational change and do that spring out into that straighter conformation. Now that straighter conformation actually forces a change in the shape of the protein itself. That change in the protein then causes a whole range of biochemical reactions to occur. And ultimately that results in an electrical potential building up on the cone cell itself, which causes a nerve impulse. The nerve impulse then carries a signal via the optic nerve to the brain. And at the brain, that image, the signal is deciphered to produce an image. So I think it is absolutely amazing that all of these molecules are doing their thing all the time while we're looking around the room, while we're looking at the world around us, and that mostly they work perfectly well. But there are times, of course, or examples where things don't work perfectly. And for the next question we're going to be looking at, we're going to look at what happens when seeing colour goes wrong. And for that, I'm passing you back to Kathy.
Thanks, Kerry. And it really is exactly as you said, with such a detailed and intricate process, there really are a lot of things that can go wrong. So let's find out a little bit about that. Probably the thing we're most familiar with would be genetic mutation, such as red-green colour blindness. But people can also have trouble seeing their colours correctly as a result of injury, side effect of some medicines, or even disease. What we're going to do is see a little bit of what it looks like with red-green colour blindness, or possibly even when blue goes wrong. So we'll start with a very basic diagram. When we see the cell types, my apologies, I just lost my place in my head. I was a slide ahead. So back again, Kathy, here we go. When the cones go wrong, there's a really fancy name for each one that can go wrong. When the red ones go wrong, that's called protanopia. When the green ones go wrong, that's called deuteranopia. When the blue ones go wrong, that's called tritanopia. Now, it's most common that something will go wrong with one of the cone types, but sometimes people will have trouble with 2 or possibly even 3. And when I say about cones going wrong, it's not that they've disappeared. It's usually they're there, but they're not working properly. Now we might try looking to see what happens when they actually have gone wrong. So in the top center of this slide, we can see a basic rainbow diagram, and that's what we would describe as being visible to someone with normal color vision. But if we look on the top right, we can see what that same rainbow would look like to someone with damage to their red cones, with protanopia. The rainbow looks very different. It's mostly now in shades of blue, yellow, and khaki. If we look down to the bottom left, which is green cone damage or deuteranopia, the colours are very similar, blue and strange or unusual shades of yellow and khaki, but with an unusual purple as well. There is a reason that red cone damage and green cone damage look similar. That's because there is a lot of overlap in the absorption ability of each of those cone types. But look at the bottom centre of this diagram. Tritanopia or blue cone damage. The world looks very different. It's in shades of red, pink and green. And as we've suggested since the beginning of this presentation, some people don't see any colour at all. Their rainbow would be in shades of grey. The technical name for that is achromatopsia, which literally just means not able to see colour. But we don't usually see rainbows just like this when we look in the world. We see the world. So let's look at some examples of what the world can look like with these different cone damages. So on this slide, we can see 4 sample images. They each contain a photograph of a butterfly, and they contain that same diagram with the number 74 that we looked at right near the beginning of our time together. The one on the top left, normal vision. But see how the same butterfly looks to someone with red cone damage. The butterfly didn't change too much, but look, the flowers aren't pink anymore, and the leaves in the background are no longer green, and there is no sign of the number in the circle diagram with the dots. If we look at the bottom left with the green cone damage, again, it does look very similar to the consequence of the red cone damage. Butterfly not much different, but the flower and the green leaves have lost their colour, and again the number 74 isn't visible. But look how it looks for someone with blue cone damage. It's so different. The butterfly changed colour, and look, the leaves in the background have changed to a silvery blue. And look how clearly they can see the number 74. Let's look at just one more example of this. It's just cute. Green frog with a yellow belly and red eyes. For someone with red cone damage or green cone damage, the frog looks very similar. The frog is almost all yellow with brown eyes now. And for someone with blue cone damage, if I was talking to someone with that damage and I said, oh, look at that cute green frog with the yellow belly, they might look at me and say, do you mean the blue one with the pink belly? And we might look at each other and think, are we even talking the same thing? Which could bring up a really interesting question, which is I think you can start to imagine now. There could be lots of problems that can happen when people can't see colour accurately. So I wonder, let's just do a quick message in and get some ideas. What problems can you imagine if you can't see colour accurately? So we'll only have a moment to catch a couple of them, but send us in some ideas that you have. Traffic light colours, absolutely, huge problem. Not driving vehicles. What else? What else do you imagine? Oh, food. Oh my goodness. Wouldn't it look different? I think actually we could go to the next slide and we can start to imagine some of the exact things you've said. As you said, food would look so different when we can't see colours properly. Imagine fashion. Imagine trying to choose your clothes. I've known a few men who were colourblind and they needed their wife to choose their clothes for them because they would pick some otherwise unusual colour combinations. But also jobs, as you said. There have been many people whose childhood dream had been to be a pilot or a fireman or an astronaut, but they weren't allowed because for them seeing colour is critically important. But that's problems that would come just from missing a bit of the colour. Here's another question for you. What if you couldn't see colour at all? Well, I'm going to share with you a short version of a very famous story about a place where a lot of people can't see colour at all. And it's from a very famous book called The Island of the Colourblind by a great scientist called Oliver Sacks. The island is called Pingelap. And as you can see on the map here, it is north and east of Australia and Indonesia. And on this island, 10% of all the people who live there see no colour at all. Their world is a world of black and white. Compared to everybody else on the planet, if we took their percentage of who sees in black and white around the rest of the world, it is 0.003%. And we might think, why is it 3,000 times more on this island? Well, to answer the question, like many answers, looking to history can help. And you might have been wondering, why is there a crown on this picture? Well, you'll see it has something to do with a king. In 1780, there was a really big tsunami. It killed almost everybody who lived on this island. Only 20 people stayed alive. One of them was the king. Now, like kings from some places, some cultures, and sometimes in history, this king was allowed a lot of wives. Now, with only 20 people left alive, there's probably not many women to choose from. But the king got more of the women than anybody else, which meant he had more children than everyone else. The king was completely colourblind. Now, like does happen in some places in the world and has certainly happened in history, the people who live here only really like marrying people from their own community. And what that's done is made this condition become extremely common, so that 10% of people alive there today deal with it. And as you can see from the two men in this photograph, they're squinting in the bright sunlight. It really hurts their eyes. They wear heavy sunglasses, and actually they'd rather sleep during the day if they can, because what they've got is something most of us will never have, is amazing night vision. They can't identify the fish species by the colour, but they can identify them by the pattern. So they do their fishing at night time, and they can see by the light of the stars. Now, I'm sure this problem is so serious medically, there probably isn't an easy way, if any way at all, we can help. But if we think back to when people have damage with maybe just one of their cones and maybe it's not so terribly bad, Fun, from your experience in physics, is there something that can help people who've got like a bit of colour blindness?
Well, the short answer is yes, with the help of filters. Now, color filters can play a part in the way colors are seen. So they transmit only some wavelengths and absorb all others. So a red filter will darken all other colors while allowing the red color through, plus some orange and yellow. So if you have got at home some cellophane paper and colored pens, draw a very colorful picture and then view that picture through those cellophane papers. This is how a filter works. So how colored filters affect the color we see, what we see. Let's say we look at an orange car through green glasses, So let's look at the next slide. A white car in white lighting appears white because all the wavelengths are reflected off the surface. But when you view it through yellow filter, the white surface appears yellow because the yellow filter allows only the red and green wavelengths through it, and they will combine to produce yellow. A sky blue or cyan car under white lighting will appear sky blue, but when viewed through a yellow filter, will appear greenish. This is because the cyan color is made up of green and blue pigments, and only the green pigments, the green wavelengths are allowed through the yellow filter without being absorbed. So color blindness correcting glasses are eyeglasses with specially tinted lenses that can help a colorblind person distinguish between reds and green wavelengths more accurately, specifically those who suffer from protanopia and deuteranopia, as mentioned just now by Kathy. Now, colorblind glasses do not cure color blindness, nor do they produce 100% normal color vision, but they do enhance and partially correct certain color vision deficiencies of a colorblind person. So the tinted glasses will act like a colored filter. They will filter specific wavelengths of light before the filtered light enters our eyes. The result, a more accurate color perception, because now the brain can see or distinguish better between the red wavelengths from the green wavelengths. But of course, this will not help those with complete damage to their red or green cones. Now, I see a question there. Yes, there are colored glasses for colorblind people, but it doesn't always work. Now, today's presentation shows how the three areas of sciences help us to understand more or understand better about what color is, how we see color, and why we see color. So I hope this highlights to you how we can all obtain a better understanding of the world around us and the universe too, if we learned it from the three different perspectives.
Well, thank you very much, Dr. Fun, Dr. Catherine, and Dr. Kerry. I just find that totally fascinating and interesting, such a simple thing that we take for granted, so many complex interactions happening at the same time. We've had some excellent questions while you've been talking on the chat, and I'd like to open the chat now for some questions. So if you would like to ask a question directly to our lecturers, students, please raise your hand, and I'm going to select some students to open their microphone. The first one, I'm actually going to ask Marcelino Solanda, who had an excellent question that he posted. Marcelino, can you raise your hand and I'll turn your microphone on. Marcelino, if you're there, here we go. Marcelino, I've just allowed you to talk. Go ahead and ask your question.
Hi, Dr. I'm Marcelo. I'm from Indonesia, precisely in Medan. So I'd like to ask two questions. The first one is, what's the difference between red, green, blue, and red, yellow, blue, RGB versus RYB? Why is RGB more prevalent than RYB? Because in our school, especially in primary classes, we learn that RGB is actually the primary classes because can actually make green from blue and yellow. But designers and designers all over the world use RGB, right? Why is that so? Why is RGB more preferred? And that's the first question. The second one is that you mentioned that
Marcelino, I might just jump in and let the lecturers answer your first question quickly if they can.
Sure.
Okay, I think I can take that. Now, RGB is for light. RYB, which is actually CYMK, is for pigments, or the colors that, the paints that you use at school and all that. I hope that answers that.
Okay, Marcelino, second question. Make it quick. We've got a few more students here. Go for it.
Okay, sure. So you mentioned that blue color and the red light will appear black because it doesn't absorb red light. But isn't in the real world the color would look purple? What causes our eyes to see the blue color and the red light to be purple?
It all depends. Yeah, and it all depends on the pigments. What is making up that color. When you say blue, there's so many different blues, different mixture and combinations of pigment colors to produce that color. So it all depends.
Fantastic. Marcelino, thanks for your questions. It sounds like you have a whole range of really interesting insights into this area. It tells me that you've probably studied sciences at your school. Thank you for your question. Let's go to the next question now. I'm going to open the microphone of Nila Azakia Hakim. Nila, go ahead. Nila, I've unmuted your microphone. Go ahead. No, Nila's having problems with her microphone by the sounds of it. Let's move to Catherine Tan. Catherine, are you able to open your microphone?
Hello, yes, I got two questions. Let's say that there's one people who have blue eyes and there's one people with brown eyes. Do they see color differently? Is it darker or is it brighter?
So I think the question is,
and then
do different people...
The second one.
Sorry, go on.
Do you want to answer this one,
and then the
Kathy?
second,
Or
sure.
Oh, sorry.
Question is, what color do people with heterochromia iridum see?
I'll start with the
That's
first
all.
bit. I'm not sure the technical name that you just said, but the colour at the front of our eyes has no connection with the colours detected by the retina. It's a whole different thing. So blue eye people, brown eye, green eye, if the cones work okay, see the world exactly the same. So I can answer that bit. Kerry, were you able to pick up the technical word? And if so, do you know anything about that? Was
what was the word hetero? Oh, is that, are they the people with the...
what that was? Yes.
Yeah, the people with that have...
Yeah. Well, Kerry.
Yes, all right. So there are people that have, let me see, women that have an extra opsin protein. So sorry, I've moved over to chemistry again, but normally people have those three cones. So you have your three separate cones with the three opsin proteins that allow you to detect those three main wavelengths of light that I talked about earlier on. There are some people, some women have an extra opsin protein. That then means that they've got like, it's like a fourth cone that can then detect another wavelength of light. And so these people apparently can see many different hues of color than a person with normal color vision can. That's quite interesting. You want to add anything in, Kathy, on that one?
Oh, well, it was actually just from when you were talking about this, when we were preparing, about the woman who was looking at the sunset and would see all these amazing, crazy, purpley, bright colours that most of us would be like, what colour?
Yeah.
But then there's colour that they can see that the rest of us have no idea about.
Very interesting. Let's go to the next student here who's got a question, and it's Tu Tao from Vietnam. I'm going to open your microphone, Tu Tao. Go ahead.
I'm Tu Tao. I'm from Vietnam, and I have this question I have always been asking Siam Cha is, why do men and women perceive colors differently?
You or me, Kerry?
You can have a go with this one.
All right, and of course join in if you want to add anything as well. So the reason for the red and the green colour blindness having a difference between men and women? Is that what you're talking? Or are you talking in general, men and women see different? Let me just
Yeah,
check.
I'm asking why men and women see different.
Oh, in general. Oh, that is a whole different question. So I can answer about the colour blindness, but I actually don't know for sure why women and men disagree.
Do you know what I think on social media, Dr. Kathy, social media, there's been a lot of these experiments where, you know, what do you see? Which colours do you see in this dress? And there was examples where people would see a blue and other people would see a yellow.
Yeah.
Did the rounds on social media there quite a bit.
No, I misinterpreted the question. So I've got an answer for my version of the question, but not the students, I'm afraid.
Yep. Okay, let's go to Dan Voltan. Go ahead.
All right. I would just want to ask that if you think in the future there will be a possibility for a permanent cure to color blindness.
I do. I think that the more that we know about the way that the molecules work in the cells and exactly what's happening, then the better are our chances to be able to repair problems. And especially with the way that genetic engineering is moving in these days, particularly in colour blindness, it's often a case, well, it's generally a case that one of those opsin proteins has not been made properly. So if we move to the point where we are able to perhaps genetically engineer so that people's cones can produce the appropriate opsin protein, then yes, that will be cured. And I think that will happen in, probably in your lifetime. Maybe not so much in mine, but in yours.
Well, and who knows, maybe some of the students who have attended tonight will end up at Melbourne University and work on this very research, Dr. Carey. Let's take a couple more questions, a couple of last ones, and then we'll wrap up for this afternoon. Let's go to Karen Tumbel. Karen, I've enabled your microphone. Go ahead.
Thank you so much for the opportunity, Dr. Carey, Dr. Catherine, and Dr. Fun and Ben. I want to ask a question. Why do warm lights like yellow are claimed to be safer for the eye? If you compare it to the blue light, are there any connections with the wavelength, or are there any connections with the eye itself? That's all actually.
Who would like to tackle that one? Did we grasp the question, or would you like Karen to rephrase?
Yeah.
Karen, can you just carefully provide the question again?
All right. Okay. Thank you so much. I heard that there are claims like warm lights, like the lights that towards to go like yellow pigmented, rather than the pure white light, are claimed to be safer for the eyesight, rather than like a blue tinted kind of light. Are there any connections why they said that the yellow, the warm lights are like safer for the eyesight rather than the blue? Are there any connections with the particular topic?
I don't actually have any answer for that. What about you, Kathy? Have you got any ideas?
If I can guess, the only thing that comes to mind, and bear in mind, I'm the biology person, I'm not the physics person, but all I thought was wavelengths. Is it something about the red wavelengths and the blue wavelengths that somehow the warmer tones is somehow less potentially dangerous to the eye than the blue getting up towards ultraviolet? Like I said, wild guess. I have no idea. I'll try.
And it's nice. It's nice having the three of us here because we can have a bit of a conversation about this and a bit of a discussion on possible.
It could be also the perception of the brightness. Red and orange and yellow appear brighter, and the blue appears to be, more pleasing, more easing to the eye. I'm not sure.
Mm-hmm. Well, thank you for a thought-provoking question there, certainly. Let's take a couple more questions. Misha, and then we'll go to the last question after that. Misha, go ahead.
Good evening, everyone. Thank you for the opportunity. I want to ask, is there a condition where a person can see more colors than normal people can see? And what do you call that condition?
Very interesting. Who would like to tackle this one? Are there more colors on the spectrum that we can't see yet, or that some people might be able to see?
Well, that's what we call the visible range, what we can see, and then the infrared and the ultraviolets, which we can't see. But we could, let's say, use special equipments, those like goggles and all, to detect them. Until I guess maybe evolution comes around and then we can start detecting those ranges. I'm not sure whether we can develop it within our lifetime.
And to go back to the question from our Vietnamese student before, then there are more arguments between men and women when they go shopping for clothes. Some fantastic questions there, and students, I really appreciate the hands are still going up. It's now heading on into the evening here in Australia and late afternoon wherever you might be. So we might wrap things up there. Before we do, I'd just like to mention that as the year is progressing, we're in October now, we've got intakes for Trinity College Foundation Studies starting in January and February next year. And then also in June, July, and August in mid next year. Some of you are starting to get your final results. Others are starting to get their first semester results. Now is the time to start planning your applications for 2022. With the COVID situation in Australia at the moment, well, 2022 is looking a lot brighter. We're gradually creeping closer to an 80% double vaxxed rate. And there's now lots of conversation, students in Australia, about it's almost time to start thinking about opening the borders, welcoming back wonderful students from all around the world. Some of them may be yourselves. So if you are interested in more information about Trinity College Foundation Studies or the University of Melbourne, my colleague, Mr. James, will put our contact details into the chat. Get in contact with us. We can give you some guidance, tell you how to apply, and tell you more about why the best students at Melbourne University come through Trinity College. Before we farewell our lecturers, James, some great questions on the Q&A tonight. Anything that you would like to add?
Way too many, Mr. Ben. I've been typing furiously in the background. I'm only disappointed I didn't get to pay attention to the lecture. So I missed out on all the colorblind stuff. I could hear you talking about it, but I couldn't pay attention. But the main thing is I didn't spill any soup on my white shirt, so it's all okay. But yes, lots of good questions. Very busy here. We're going to be very busy for the remaining 4, I think it is. So I look forward to that. I'll have a little workout on my fingers between now and then.
And thank you very much, James, for answering some of those inquiries from the students. Once again, if you are interested in more information about why Melbourne University continues to be the #1 university in Australia and why Trinity College students are always the top performing students at Melbourne University, get in contact with us. We've got some excellent lectures coming up in the coming weeks. Next week, we shift from sciences into finance and economics and accounting. We're going to look at the stock market. Some of our leading academics in business and accounting are going to give you some information about the stock market. That's coming up next week. But our 3 outstanding lecturers in all areas of science at Trinity College, thank you very much, Dr. Fun, Dr. Kathy, and Dr. Kerry. Students, give them a virtual clap, say thank you in your own language, but otherwise, thank you very much for presenting this afternoon. And students, thanks for joining us. We look forward to seeing you next week and to the coming lectures. So bye for now.